I got it this third year, like end of my second year.
Did you apply twice?
No.
No, you just got it the first time?
Yeah. No.
And is she on? Yes. Yeah, we'll get some more people coming in. But I thought Can everybody hear me okay? Do I need a microphone? Okay, so I'm delighted. I'm Martha Palmer. I'm actually in the computer science department and the linguistics department. For those of you who don't know me. And I'm delighted today to be able to introduce our speaker, Yanjun Gao. She's a brand new assistant professor in the bioinformatics department at the Anschutz campus. And she comes here from a 3-year postdoc at the University of Wisconsin-Madison in their medical school, where she won a very prestigious K99ROO award. I had to ask her what that was. I understand it's sort of the equivalent of an NSF Career Award. So, and I guess she brought that with you here.
Yeah,
then.
yeah,
right. She did her PhD at Penn State. And her lab at Anschutz is the Language, Reasoning, and Knowledge Lab. So she's very interested in applying techniques in natural language processing to medical informatics, which I think we're going to hear about today.
Yeah.
So thank you very much.
Is the mic working well? Yeah. Okay. So thank you, Martha, for the introduction and also the invitation. It's really nice to be here today. And actually, when I was making slides last night, I actually made an Instagram story post to say that, wow, can't believe that I'm making this today. And I was just one of you, like not long ago. So today what I'm going to talk about is language technologies, and particularly what are the research projects that we're doing in Anschutz, and what's the exciting things about them. Let's get started. Okay, so I'm going to start my talk with this really timely message that all of you know that Geoffrey Hinton actually won the Nobel Prize in Physics. And which I would like to say this is the best time for our generation to start working on AI, because we have been like inspired by so many like these greatest people in our era. And then one of them is actually, one of the major breakthrough in terms of the language technology is this transformer architecture, which comes out 2017. And it actually inspired by, it got inspiration from, famous people and their foundational work, people like Geoff Hinton and someone else that I'm sure that you can think of who are this person. And then because of the transformer architectures, we start to get like these fascinating large language models, and many of you see or have been using some of them, like this include like open box or like closed box at large language models, LLMs, across different domains. There's also this really famous discovery of scaling loss, meaning that people find out that when you increase the size of the parameters and also increase the training data size, you're going to get much stronger or much more power in the LLMs. But now the question that I really want to ask today is scaling loss all we need? is scaling laws like the only solution or the only exciting things in this field that we can work on? And if not, what are the other options? So before I start talking about my research, I do want to briefly introduce my journey because I get asked a lot how I got to this place right now. So I got a PhD admission by the Penn State Department of Computer Science Engineering in 2014. And I have 2 years of bad luck with my advisors. So I actually changed advisors 3 times. It was until 2016 that I started to work on natural language processing with my PhD advisor, Rebecca Passana. And then the type of projects I work on at that time is like summarization evaluation, discourse analysis, argumentative mining. And then one of the application areas is actually education, not medicine. So I worked on a lot of projects on like how do we evaluate students' writing using NLP technologies. And then it was almost end of my PhD, the COVID pandemic started. And then at that time that I suddenly found out that, okay, there are the things that are really important in this world. And one of them is healthcare. I have no idea where I would be or what kind of things I want to do until I found out this postdoc opportunity at the University of Wisconsin in the pulmonary critical care data science lab. So you can hear by the name, you can understand by the name that that's the front line of fighting COVID at that time, because they deal with like ventilation, they deal with pulmonary, they deal with pneumonia, they deal with COVID. So as the first day of my postdoc work, I actually went into the pulmonary ICU and saw these patients who are like on the machine ventilation, and then they're not able to breathe. They're not able to be like having any awareness, and then people have to be like in a really isolated environment to treat them. So that scenario was actually quite impressive to me, and I never imagined what the hell would look like. And that's my first reaction when I saw that. So that actually got me thinking about, okay, as a computer scientist with a PhD in computer science, what can I do? And what are the things I'm really interested in? That's why I'm here in the Department of Biomedical Informatics under School of Medicine at the Anschutz Medical Campus, and start doing AIs and NLP research on medicine and healthcare in general. I also forgot to mention that it was before the end of my postdoc, ChatGPT started to release, and that just changed the paradigm of everything. So LARK, which is the name of my lab, language reasoning knowledge, as Martha introduced, because these are the key components that my research focus on. In other words, these are the areas that all of my research inspirations comes from. In particular, I'm really interested in how human is making decisions given complex data, for example, like language or different modalities of data like images or videos or audios, and also reasoning, how people start to doing reasoning when they know, oh, they have to draw a connection between what they see or what they hear or what they were reading to their decisions making. And lastly, one of the essential components behind this decision making is knowledge. For example, it took 7 or 8 years for a student to be trained as a medical doctor. So there got to be a lot of things happening within that 8 years that we can probably have an LLM or AI to be trained on. So my talk today have 2 main components. One, I want to start with introducing some AI or NLP research that I'm doing for healthcare. And the other part, I want to talk about like some general domain NLP problems that my lab is currently working on. So let's start with the first part, and we're going to focusing on diagnostic decision making. So let me start by introducing you what is electronic health records. So some of you, if you've been to hospital and if you talk to your doctors, this is the screen that you might see that show up on their screen. Of course, like if you're not in ICU, if you're not in any like surgery units, you're not going to see a bunch of information in your electronic health records. However, for patients who are in ICUs, normally their health records are really long and really complex. So what you're looking at right now is a mock patient that have multiple hospital admissions, meaning they've been to the hospitals many times. And each time it could be a different reasons. And there could be a different like specialties type of physicians who take care of them. And then if you look at the left-hand side of the screen, you can see that most of the texts here are combined with natural language and then also tabular data or like structured data, what we call. So there are numbers, there are abbreviations, the medical jargons, There are also natural language that talk about what is these patients having, what kind of problems patients having, or like their medical histories. And then you can see that if the patient situation is getting worse and worse, like these EHR will get much longer and complex. So electronic health records, although they are designed to help to improve the efficiency of clinicians' workflow, but they're actually causing more troubles than bringing efficiency. One of the problems is, where is the most important information, or what is the most important information for that given patient, given that there could be many, many information generated when the patient go to the hospital. And that has been an issue, not only because it's like the physicians, it's harder and harder to find the most important information, but also it would cause the physicians burnout. Meaning after reading so many of these EHR records for a given patient, well, they start feel really exhausted, and sometimes they will make decisions that's not evidence-based. So you can think about how dangerous those situations could be. Like it would lead to medication errors, it would lead to diagnostic errors, and in particular, diagnostic errors is one of the areas that my work mostly focuses on. So let me talk about clinical diagnostic reasoning, because that's essentially how like a person can become medical doctor and start to say, okay, for this given patient, what's their problems? So diagnostic reasoning, like the other really complex decision making, have two system thinking. I'm sure like some of you have read this book. It's called Thinking Fast and Slow, that talks about for most of the complex decision making, people are having two types of system in their mind. So one is system one, that's based on heuristics or based on fast thinking. And the other is called system two or type two thinking, meaning they're based on like they're thinking really like rigorously and based on the evidence they can find. They will draw connections between what they see, and they will utilize their knowledge, and they're not just like doing the decision making based on their first reaction. So I want to put up this figure to show you like more vividly what that system one and system two would look like. As you can see, like the rabbit was saying to the turtle, why are you so slow? So the rabbit is actually system one thinking. It's fast, but it's not accurate. And then there's also system two thinking, like the turtle, and asking rabbit, why are you so stupid? Like you're making many mistakes that they're so obvious. So for the goal of my projects, or like for most of my research, we want to develop augmented intelligence for clinical diagnostic decision support. So you can see that I'm not saying artificial intelligence for clinical diagnostic decision support. That's because if you say AI for clinical decision support, like people are going to think that, oh, you're going to replace the physicians. And I get that questions a lot. So I like to say we are augment the people's decision making, not to replace them. And then you might also see many articles or papers or news that talk about, wow, right now we have like MedPalm, we have GPT-4, and they pass the medical licensing exam, which is every medical student have to take before they can practice medicine. And then what I'm showing here is how MedPalm 2 is actually outperform many of the human physicians in terms of the multi-med QA. So it's a benchmark for medical question answering tasks. And then we also have like human evaluation in terms of whether there's more omission coming from the human clinicians, or there's more omission from the system, or the other types of errors. So the main takeaway from this figure is that, well, people have been claiming that these artificial intelligence or LLMs are so powerful, they can potentially become the backend of health AI. But I'm going to ask, is AI for healthcare and medicine really here? The reason I'm asking that is, if you think about what medicine means, it's a science for uncertainty and an art of probability. So this is quote from William Arthur. So he's been called as the father of the medicine. But none of these benchmark or none of these evaluation that we've seen from like GPT-4 and MedPalm was actually evaluated on real patients and real HR data. And they're not evaluating on the task that the clinicians really care about. So one of the tasks that physicians care about is predicting diagnosis using the real world patient data. And that's something that I'm going to cover in my next couple of slides. And secondly, because medicine is a science of uncertainty. So how do these LLMs cope with uncertainty? How can they express uncertainty? Are their uncertainty expression or uncertainty estimation reliable? Can we trust them? These are the questions that we're going to answer in the second part. Let's start with the first part. The type of electronic health records data, you might see some papers that talk about EHR, like LLMs for EHR. Many of them focus on natural language. We did that also, but now I want to focus on the structured text, which is where like it talks about the values and then the clinical meanings associated with those values. How well does LLM really understand those things? So we did a simple probing task where we just like prompt Mistral and also Llama models to say, well, given these, like, for example, systolic blood pressure, what is the reference range? So what is the normal range given that vital signs or laboratory results, and what is the units of measurement? So it turns out that according to human physician evaluation, on a Likert scale from 1 to 5, where 5 is really accurate and 1 is not accurate at all, many of these LLMs, such as Mistral and Llama, they can have a pretty good scores in terms of like recalling this correct knowledge about reference range and also units of measurements. They can also talk about that given different gender or age of patients, their reference range might be slightly different. So that gives us a little bit confidence. Okay, these LLMs, they do have knowledge about, this basic knowledge on structured electronic health records. The next thing we did is we took the real world EHR data, which is shown in that blue table. Like normally when a patient's come in, they're gonna go through multiple like screenings or like tests. And then we took each of the patients and then look at what is the most likely diagnosis they have. And that is annotated by human experts. So we use that data set. And now our goal is to really look at, well, given those data set, can the LLMs make correct prediction to say, does the patient have a disease such as sepsis, arrhythmia, or congestive heart failure, or would the patient die during their ICU stay, or how long would the patient stay in the hospital or stay in the ICU, whether it's 3 days, whether it's 7 days. So these type of predictive modeling tasks are really common. If you look at the papers published in medical journals, you will see that people have been focusing on it for like almost 2 decades. And then many of the models they're using is machine learning, for example, like XGBoost or logistic regressions. And these models has been achieving like fantastic, well, fantasy is not correct word here, but at least state-of-the-art results on many of these tasks. And to tell you some truth, actually some of the hospitals in the United States, they would deploy these machine learning classifiers in their clinical, in their bedside as applications to say, okay, these patients might have like life-threatening events happening, and then bring up that alert so that if the physicians inside the hospital from every unit, they see that alert, they would just rush to that patients and deal with that emergency. So now our goal is trying to compare, can these LLMs being used on the same type of task as this machine learning has been using on? And then you can see that the way that we're doing it are 2 types of methods. One is looking at their embeddings, because, well, embeddings is where like these LLMs store their knowledge and feature representation from, right? So now we want to see, compared to, machine learning classifiers has been using raw data features, which is mostly like pandas data frame, that I'm sure that every one of you know. And then instead of feeding that raw data into machine learning classifiers, what if we utilize the features coming from LLM? And would that give us benefit over these raw data features, given that LLM are so powerful and they should understand most of the word knowledge, and that might bring more like useful signals for those predictive modeling tasks. So that's our assumption. And it will also compare to the direct generation, meaning that we just prompt these LLMs and ask them to predict whether the patient has sepsis, whether the patient would die during the ICU stay, or how long the patient is going to be staying in hospital. And I'm just going to share quickly on the direct generation results. They're not good at all, even though we have pretty good performance, like just by prompting them to say, well, what is the reference range on this like tabular data, but they're not good at predicting whether the patient would die or no on this real patient EHR data. So now we shift to like looking into the embeddings and then plus machine learning classifiers. And we also try different LLM settings. For example, prompt engineering would actually say to the LLM, well, imagine you are a medical expert. Imagine you are an AI generating useful features. We try all these, like basically every combinations of persona that you can think of would be relevant to this task. We also try like few shot train of thought and then parameter efficient fine tuning. So I have results for the PEFT because I know that's some people might ask questions on those. But the short answer is that, well, the out-of-box LLMs, you just do nothing. Like basically do not do prompt engineering. Like just by feeding the input to the LLMs, that would give you the best performance on this task. You can also see that we try different table to text conversion methods that include narratives or JSON or Markdown or XML or HTML format. So what you're looking at is the major results coming from these experiments. And then we are comparing with raw data plus logistic regression and random forest and XGBoost. So these are the three common types of machine learning classifiers you're going to see from this like predictive modeling literatures. And in fact, XGBoost has been achieving state-of-the-art results for like many years. If you look at like clinical deterioration prediction or length of stay prediction, and they're really hard to beat. So when you look at the LLM embeddings plus XGBoost or plus logistic regression classifiers, you can see that the green highlighted fonts are the ones that have confidence intervals overlapping with these best performing classifiers. And sometimes like that difference is quite minor. For example, like Mistral 7 billions with no prompt engineering at all can actually get like 71.12 AURC scores compared to the XGBoost results, which is only like 0.05 improvement. But then there's also task or like prediction that's like LLMs are performing really bad. For example, like the arrhythmia. So sepsis, arrhythmia, and chronic congestive heart failure, these are the three common types of diagnosis that would cause patient deterioration. Meaning that if, let's say, like a patient is dying inside ICU, then these are the three common reasons why they are causing their dying. That's why we focus on these three diagnoses. And then when we look at the PEFT with QLoRa, so what you're looking at is 4 confusion matrices, and each row represents one task. So my right-hand side is the Mistral without QLoRa, but then the left-hand side is with QLoRa. So one thing that you can quickly see is because of this like imbalanced data sets, imbalanced label distribution, like after QLoRa, it actually make the Mistral predict less true positive and more true negative because there are more true negatives in both of the data sets. That makes sense, right? Because like most of the patients, they were like being discharged safely. There's only a small portion of the patients would die in hospital in this case. And same with the next, same with the lower row, which is the mortality prediction inside ICU. So that task was about, well, if the patient is going to die in the ICU, and then the true positive becomes 0 after QLoRa tuning, while before it was like the Mistral can predict 6 cases on those situations. So what I'm trying to conclude here is that there's definitely more work that we will need to do rather than just saying that, okay, these like LLMs have been achieving so fabulous performance on MAC-QA. It's completely different things if you think about this benchmark data set and what's happening in the real world and what's really needed in the real world. Now I want to move on to diagnostic uncertainty because these two topics are actually continuation with each other. So diagnostic uncertainty is shown by this figure. It's actually talk about, well, there are actually 2 components for diagnostic uncertainty when we talk about it. We have the pre-test uncertainty. So the pre-test diagnostic uncertainty is between 0 and A. So that portion is given the patient's like first impression, like they come in and then they complain about what problems they're having, they're feeling bad, and like they cannot eat and all these things. So that is the first reaction that these physicians will come up with to say, okay, what is the likelihood that patient is having sepsis or pneumonia or something else? And then because of that pretest, depending on the test threshold or like how severe the problem is for that patient, then the physician would decide whether they're going to start prescribing diagnostic tests to say, to confirm, further confirm whether this is COVID, whether this is pneumonia, or whether this is sepsis. So that is where the post-test probability would come from. And once they get the post-test probability, they have a more, like a higher confidence to say, this patient is having sepsis. That's why we are we're going to prescribe some treatments to cure sepsis, or we're going to prescribe some treatments for COVID, blah, blah, blah. different disease have different diagnostic threshold for the testing. And then you can think about it's a really different thing when you say a patient have like 20% probability for pneumonia versus 20% probability for obesity. So pneumonia might not be a good example here, but if you say somebody have 20% as, I don't know, like some disease that would actually cause them dying, then it's definitely another thing than to say that 20% of the probability is being obesity, right? Because obesity is more accurate disease. So estimating these pretest probabilities is really hard because you have to think about, well, the prevalence of such disease and what is the patient's presentation, and then what's their like histories. So they're like, if you remember what I was saying early on, like the electronic health records contain complex and rich information. That's where like the decision has to be made based on those rich information. And in fact, clinicians are perform poorly on estimating pretest probabilities. So that's one of the reasons why we have so much of the diagnostic errors in this country, because like physicians are either overestimating some disease or they're underestimating some disease. And then one of the study actually evaluate GPT-4 just by prompting them and ask what is the likelihood of that patient having some kind of disease. And you can see that like the blue line is the true range. And then the yellow line, the yellow curve is the LLM's prediction, while the gray is the human. So human has a much wider estimation in terms of the probability, pretest probabilities, versus like LLM has a much narrower one, but none of them is actually close to the true range. So that got us to think, well, is next probability of LLM really the pretest probability? Can we really use it as the experiments show in the previous slides? If you think about LLM, what it does is the last layer, it's just going to take whatever the representation in the last layer and projected that to the vocabulary space, and then pick the words, the next token that has the highest probability, right? So if you prompt an LLM to say, okay, what is the probability of that patient? What do you expect it to say? Like, can you really trust the number that they outputted? I don't think so. So we actually look at literatures, especially in natural language processing, and there is a recent survey from NACO, and then that talks about like both white box and black box LLM and their common methods of estimating confidence, which include looking into the internal logics of those tokens, or like looking at their internal states, or like having another surrogate model if it's a black box model, or like just prompting them multiple times, and then you take the average answer as the like the confidence. And then we applying this similar technique to this like pretest diagnostic probabilities problem, where we start looking into not just the embedding plus machine learning classifiers, which is attributes in this case, also the internal token logics by prompting the LLM to say, does the patient have sepsis? Yes or no? And then we measure the logics of answering yes, logics of answering no. And then we also have the verbalized confidence, just simply prompting to say how likely the patient have sepsis, for example, and it gives us a confidence range between 1 to 100. And then this figure is reporting AURC scores. And in the top row is from Mistral, and the bottom row is from Llama. There's additional experiments that we did, as you can see from the x-axis. So we add in different variables that might inherently like bring up the bias inside these LLMs. So we actually, well, the default setting is we don't tell the LLM like the age or the sex or the gender or ethnicity of that patient, but we add in these variables in our subsequent experiments to see how much impact does these bias variables would cause on these predictive modeling tasks. So it turns out that, first of all, the token logics and verbalized confidence are the two most common ways of getting confidence estimation from LLMs. None of them actually perform well. Like if you look at their AURC scores, they are like below 50 most of the time. And then embedding plus machine learning, as we show in the previous experiments, they're actually quite good, although not as good as the raw data plus the attributes baseline. And then adding in these different bias variables actually help or actually change the model's prediction, but it really depends on what models and what diagnosis. So it's really a mystery, like what actually brings up this model's prediction and why the models make such decisions. And in these slides, we actually correlate like the positive class prediction, positive diagnosis predict probabilities from LLM and correlate them with the raw data plus attributes baseline. So by doing that, we want to see, let's just assume that the raw data plus attributes is a silver standard baseline or silver standard prediction. Then how well or are these LLMs as uncertainty predicted in the same direction or in a different direction? So it turns out that only the LLM embeddings plus attributes is predicting on the same direction versus the other one, like token logic and verbalized confidence, they have negative correlation with the baseline results. And in the last set of experiments, we actually look at the expected calibrated errors. So the less the numbers are, the better the performance would be. And then we compare to the raw data plus attributes, which is our baseline here. Then you can see that especially verbalized confidence has a terrible error rate, has a terrible ECE here. And that brings up to our future direction for this work. So we want to develop LLMs that calibrated for this diagnostic decision support or decision-making systems. And by doing that, we can actually help to augment the physicians for their like either two types of thinkings or whatever the decision they have to make to conclude the diagnosis. And there's another work that we're concurrently doing, which is associated with the diagnostic decision support, which is called the knowledge grounding and fact verification to reduce hallucination. Because one of the troubles we know before we can really safely deploy these models is that we don't know how much hallucination they're going to get in their output and how consistent their outputs would be. And the only way, or one of the ways that you can do it, is to verify their knowledge or verify their output to say whether that output is actually grounded in the knowledge base. For example, like EMLS is one of the largest medical knowledge repositories in English medical concepts. So currently we're actually working on neurosymbolic methods to replace graph neural network for this work. Okay, now I want to move on to the second part of my work that talks about these like foundational NLP problems that we're working on. So these include two types of work that I want to briefly talk about. So one is about discovering knowledge gaps in scientific literatures, and that is coming from one of my PhD students, her thesis. And then the other is something really new right now, which is called mechanistic interpretability. So first, let's start with the ignorance detection project. So what is ignorance that I'm talking about? Ignorance is defined as something kind of like a knowledge that we know that we don't know. Like it's about the absence of fact, understanding, insights, or clarity about something, or like not individual lack of information, but on the entire community, what we don't know. And ignorance is, when we talk about ignorance, it will be the same as knowledge gap and non-unknown in my next couple of slides. And then let me give you an example of what considered as the ignorance or knowledge gaps. So this CRISPR-Cas9 is a like genomic editing method. So before CRISPR-Cas9, the soft gaps or people know about like bacteria adaptive immunity or like precise genome editing. But the things that they really don't know is how this like bacteria has been delivered or like the delivery mechanisms or off-target effects. But because of CRISPR-Cas9, they're able to close those new gaps. And that's what we call like the ignorance or like knowledge gaps. So there are different types of knowledge gaps. And one of the things that we're particularly interested in is what is the future work that we can conclude from what people have done. And the two types of knowledge gaps or future direction that we're looking at are like explicit mention. Like sometimes like you will see in that paper that somebody talks about, well, this merits future investigation, right? Like at the end of their experiments. Or they will talk about a couple of things, and then you can kind of get it from reading their work to say, okay, these are the things that they're gonna do in the future. These are the things that is the future gap or future direction for their work. So that's called the implicit understanding from the context. So sometimes the context could be paragraphs, could be like the whole paper levels. And then the experiments I want to talk about here is about extracting knowledge gap, and in particular, extracting implicit knowledge gaps from the entire paper. And then to be able to perform this task, we actually annotate 24 research papers And then we recruited 18 participants, and these participants are the authors of the papers that we included. And then Nora, who's the author of this work, like she actually annotate like on lines or sentence or paragraphs, and then to identify the knowledge gap, and then use that to prompt a GPT-4 and also a llama models. But here, what we want to show mainly is on the results on the GPT-4 models, because it's amazing. So once we extracted these knowledge gaps, or we asked GPT-4 to conclude these knowledge gaps, we send these knowledge gaps back to these authors. And then we ask them these following questions. Is this extracted knowledge gap like factually true? Like, is this something that like we really think is a gap? Or do you agree the ignorance statement is still an open question? So is this question being solved already, or it still remains unsolved? Or could addressing these gaps significantly improve the field, or how significant are these knowledge gaps are? It turns out that there are 83%, over 83% of the answer of the participants says yes to the first question. So these knowledge gaps are truly exist. They're factually correct. And then over 56, about 56% of participants say that they think those gaps are still an open question. And finally, 67 of them think that these knowledge gaps are significantly, like there's significant problems and need to be solved. There's another slide that I did not include here, but many of the participants gave us feedback to say that, well, they did not pursue that knowledge gap because either they don't have fundings to do that, or it's no longer their interest. But nonetheless, like GPT-4 in this case, are still able to conclude from this implicit mention of knowledge gaps across the papers. And now I want to move on to the next part of this talk, which is the mechanistic interpretability. The reason I mentioned it is because the more I learn about mechanistic interpretability, the more I feel like they're going to be useful for many of the research in NLP. So we start with, because it's a really new field, as some of you might know, so we start with a really simple and dumb question, which is called the positional bias in multiple choice question answering. So positional bias is the thing that when you, for example, when you evaluate an LLM on the MCQ, a multiple choice question answering, they will always pick an answer A in this case, regardless of where is the correct answer, or regardless of how the answer options are being shuffled, which is a really dumb question, right? So we're really interested in knowing why these models would do that. And we start with GPT-2, which is really small models and open source models. And then, so the way that we're doing is we first visualize the circuit flow inside the LLM. So basically, you can using mechanistic interpretability and some toolkits from that field, you can visualize the logic activation when you feed in input, and then what is the what has been the most logics assigned to that answer on each different layer. And then by doing that, you can actually measure the absolute difference between the correct answer logics and the logics that currently has the most weight on. So that's where, if you look at the first picture, that's where like the percentage is coming from. So if you look at the MLP in one of the box, it says 68.6. So that is like, well, how different is that logics compared to is the current predicted logics compared to the correct answer logics. So the well, actually, how correct, not how different. And you can see that at the end, the later the layers is, the more errors or the less correctness like that logic would be assigned to. And then we also we can visualize that internal logics in like a heat map way. So each row is a different input. And then the blue means that it has a really correctness compared to the correct answer logics, while red meaning that it's really far, like the logic prediction inside the LLMs is really far from the correct answers. And we can identify, at least for the GPT-2 XL, that most of the errors occur in the last two layers. But how are we going to correct them? We don't have an answer yet. That's still an open question and on the work in progress work. But the reason I bring out this work is I do think that this field has a really great promise in help us answering a lot of the questions, although like coming up a good intervention, it's a really hard task. So that actually concludes the research part of my talk. And I do want to talk about like there are some other really exciting projects we're doing right now, which include like the safety explainabilities, because you can think about these are the, well, if you look at the entire field, these are the things that people are really focusing on right now. And also the AI, human and AI or AI and AI interaction. So I don't think that AI can make decisions by themselves, especially if you think about like healthcare situations. Like every AI output has to be evaluated by clinicians or human experts, right? So even though we have like, there was a recent project that I did with a healthcare system where we designed a prompt engineering framework, and then we use that to prompt GPT-4 and then to generate patient message response. So where whenever there is a patient email comes in, we use GPT-4 to answer those emails. And even on that simple task where like patient's message is always about medications, when to schedule appointments, oh, I suddenly hurt myself, what should I do right now? All kinds of like questions, but they're really in a narrow scope. Even on those cases, like every message generated by GPT-4 has to be checked or manually verified by a nurse or physician. So I do think that in the longer run, like AI or an AI interaction, human AI interaction is something that we're definitely interested in pursuing. So finally, I just want to really thank Martha again for this invitation. And I do want to say that to all the students, that I do feel that you're really lucky because like Stu Boulder and the NLP group are fantastic. And as my early stage as a PhD student, I read a lot from this group. I read tons of papers from this group. I got a lot of inspirations, and that actually formed my early idea of what that NLP would look like until 2022, ChatGPT came out. But still, like deep in my heart, I still feel like most of the theories by Boulder group is still like they're really wonderful. And then there's only one thing that I do want to say to the students, which is this is the best time across all areas, across all years to do interdisciplinary work. It never becomes so easy that you can collaborate with somebody outside your field. Like I collaborate a lot with physicians or clinicians. We don't speak the same language at the beginning, but now because of ChatGPT or all these fabulous technologies, you can show your ideas in a way that they can understand, or they can start doing programming, and then you can provide consultants or advice to them on more exciting projects. So I do think that although people say that like computer science and AI has become so competitive these days, I do think it's true. But I also think that there's so many other like really exciting projects that we never had a chance to think about, but now it's finally our time to start doing that. And we are able to do that because we know computer science, we know these basic principles in NLP, and we also know how to talk to them. And I do think that, like, I hope that some of you in the future, in the longer run, can start doing things, like NLP for sociology or criminology or like for healthcare and other stuff. So a really important slide, maybe most important slides. So currently we have 3 lab members and we are actively hiring research interns. There definitely PhD opportunities, but I don't think that some of you might be interested in it because the PhD program I'm currently in is called computational bioscience, although I know nothing about bioscience, but that's where I got put in. Okay, that's my last slide. Now I can take any questions you have.
So thank you very much for that. Mark, that was a lot of information. So we have some time for questions now. So maybe I'll start with the question. So I think I missed what you said when you're talking about the knowledge gaps, and right at the end, you said something about the LLMs and the knowledge gap, and I kind of missed that. Could you go back over that point again, please?
Yeah. Is this slide or the next slide?
It was the last slide, or even maybe this was the last one.
Yeah.
Yeah, it was on this slide right at the end, and you just said something about either the LLMs could identify the knowledge gaps, or I didn't quite catch it.
Yeah, yeah, thank you for catching that. Yeah, when I say that, I was a little bit confused myself because there are many things going on in that problem right now. So we were surprised to see that GPT-4 can achieve like 80%, over 80% of like true knowledge gaps extraction. And then we are also surprised to see that like the gaps that extracted are still being considered as significant, which is like almost 67% of them. So there was a debate actually in our campus right now, which is about how AI is actually like shaping critical thinking of like science right now. And then the reason I mentioned is because there was a recent Nature article that cite the director of our graduate program in our campus. But then it was cited in a weird way to say that we don't support students using AI, but it is not true. And then our work as one example of, well, we encourage students to use AI and then to explore AIs, and in particular in doing science, in doing like research. But the way that we using it has to be like, we have to train our students in a way that they can enhance their critical thinking using AI, not to use AI to replace their critical thinking. So it maybe that was the cost. And when I was saying these slides, I was thinking about that. So that maybe that's where the confusion comes from.
Okay, so there are still, I mean, I totally believe this, that there's so many things we don't know. There's tons of gaps in our knowledge, especially in medicine.
Yeah.
And you think the LLMs are going to help us fill these gaps? Or what was the point you were making about the role of LLMs and addressing the knowledge gaps?
Yeah, so we're trying to say that, so LLMs can be used kind of like a personal assistant in a way, or that help you to capture these gaps that you might thought about, but you don't remember after a while, or like you're not longer interested in them after a while. And then the input to these LLMs has to be coming from, you know, people's papers, right? And then, but like, well, they're able to extract it. We're surprised that they're able to extract these gaps, but we also think that there got to be a role for these LLMs after extracting these gaps, and then to spread out to the whole community to remind people that these are the questions that we still don't have an answer yet. These are the open questions that still require people's time and efforts devoting to solve them. And it shouldn't be just sit in somebody's mind until somebody who, when walking and then suddenly come out, oh, this is some questions that I should have worked on a couple of years ago after I wrote a paper, after I found something. So that's where like my that sentence was coming from. Yeah.
So I had another question. So that was really interesting where you were showing the different layers of the LLM, and where the blue was where it was more or less close to getting it right. And it was blue, and it was blue, and it was blue, and sometimes it wasn't quite right, but it was blue, and then right at the end, it was totally wrong.
Yeah. Yeah.
So do you have any intuitions about what might be going on with that?
That's a really good question. And the answer is no, because what makes this problem hard is like, this is just for GPT-2. And GPT-2 have the same patterns across different sizes. So GPT-2 small, GPT-2 XL, L or XXL, they all show the same behaviors that at the end, they start making mistakes. But when we look at the other LLMs, for example, like larger ones, we start noticing that red cells actually come early on rather than having it at the end. So that made me think about, well, one thing that we want to do right now is to detect where those knowledge has been stored, whether like the location, for example, which layer, which neurons that store those knowledge. And then maybe there's something wrong when they recall this correct knowledge from these locations. Maybe they got confused about the prompts, maybe they got confused about the question. That's our assumption currently.
I also had a question about this. Like, how did you, like, you mentioned that the percent is supposed to represent correctness. How did you measure that?
Yeah, so we are measuring like basically across all the samples. Let's say this was based on like 50 samples or 100 samples, I forgot. But we just look at the absolute difference between, for example, the first MLP layers, then you get like the logic that predict on one of the answer, and then measure that difference between that correct answer, what the absolute correct answer logic versus the model's current prediction. And then we count, well, what percentage of the time that layer has made the correct choice. And then that's where like the percentage is coming from.
So you take the language model and then you take each layer, you train a classifier on each layer?
No, you just look at the logics on top of it. So basically the weights, the MLP layers has the weights, and then the weights would assign to the correct answer or the incorrect answer. And then when you have the correct answer, you can measure like the logic difference. I guess you're talking about in terms of the output, like vocabulary and then the logics on that, but I'm talking about like the weights, the difference of the weights. Does that make sense? So maybe, yeah, sorry to confuse that, but let me repeat myself or like say in a different ways. It's on the weight difference. It's on like the difference of the weights assigned to the correct answer and the weights assigned to the incorrect answers.
So if you got the correct answer, you know what the weights are when it is producing the correct answer. So you're just looking at the differences between those weights and all the other places.
Yeah. Yeah. Does that make sense?
I think, aren't you encoding tokens and then on top of the final layer, you're training a classifier?
We don't train classifier. You can just grab like the internal logics. So for example, you have A, B, C, D, and then you know.
Oh, okay. Which is the language model vocabulary. Okay,
Yeah, yeah.
Makes sense.
Yeah.
Yeah, I don't know a lot about transformers, but I'm just wondering, as you change the size, or if you have the same model, is it that the inaccuracy is always by virtue of the way you're training the whole system gonna reside in those final layers? Because yeah, you could also just imagine truncating the layers and maybe sampling from an earlier stage, but maybe those are less of a quality answer or get less of what yeah, maybe it's you get a higher quality answer, although less correct potentially at the final layers when that's necessary. I'm not sure.
Yeah, that's also a good question. Again, that's what makes this problem really hard. So we try different model editing methods. So model editing has been like, if you look at like ACL or EMLP, there's always papers that talk about model editing for factual knowledge, association, that kind of things. So the idea is that you change the weights of where that layer causing problems. Either it's zero out the weights or like you always put like kind of like a constant and then kind of shift the prediction to a correct spectrum. These are the techniques. But the problem with those techniques is that if you're going to change the weights, you're also going to change the prediction on the other tasks. You're going to lose the generalizability because what the model has been trained on or during the pre-training process, they're remembering the knowledge inside those weights, right? So if you just like correct or added some neurons, what if next time you have something similar where you have like nearby there's other knowledge storing, and then because you change the weights of a neuron and then you're leading the other prediction which used to be correct and to be incorrect right now. So that's why like we try model editing and then it doesn't work. Well, at least it worked on the problems that we're working on, but then we lose the generalizability. Yeah.
So it's not like CRISPR and G code.
No, no.
Do you worry at all, or have you seen at all where the medical data that you work with doesn't necessarily represent like a diverse group of people? Do you like fear that there's going to be bias baked into that data that then comes out in a product that you give to a healthcare provider?
Yeah, that's a really, really great question. Yes. So here's what we normally talk about when we talk about, like, for example, LLM that train on the giant corpus of data from a hospital. So for example, University of Florida have their own LLMs that train on the entire Florida's patients. And then we say that you cannot apply that LLM to, for example, Wisconsin or Colorado, because the population and diversity is completely different. In Florida, you have more elderly patients, while in Colorado, you have more like, you have a balance or slightly more balanced distribution across different ethnicity or like different gender, or even age groups. So definitely like the predictive model, that's also what makes the predictive modeling really hard, because at some point, you want this bias because they are the like strong indicator of something. That's where, like, for example, Black and white patient, they don't share the same reference range for some of their vital signs. But you also don't want it to be so like specific to a population group that you cannot generalize it to the other groups. So that's a really wonderful question, and I don't think we have like a standardized solution to it yet.
So I think you mentioned that you repeated this like positional bias research with newer, larger models, and that the inaccuracy in like the logics and the internal logics actually started appearing in earlier layers in the larger models. Did I assume also though that probably the newer larger models also like exhibited higher overall accuracy on those on those like question answering tasks? Do you have any like insight into how those two things kind of can coexist? Like it's introducing it's introducing error earlier, but producing overall better results still.
Yeah, that's a really good question. So, we noticed that on mixture 7 billions, any models that's about 7 billions, they don't have these stupid errors anymore. Like they're smarter than GPT-2, let's just put it this way. So, but they do like on some tasks where it's really knowledge intensive. For example, we ask them like, well, given a patient and an ABCD, what is the diagnosis they have? They still show that behavior that like they always pick A, regardless what's the correct answer or answer shuffling. But that's where we notice that the knowledge actually come up earlier rather than later. But still, that's another different question because the domain is different. Like the domain of knowledge that we're looking at is really different from GPT-2. But GPT-2, we didn't do it on medical knowledge because they failed at this basic MCQA tasks. So what I'm trying to say is like, the thing that we are really struggling with is to come up with a evaluation framework or framework that be able to say that, okay, whatever the LLMs that we work on, we always can detect this type of errors. But as you increase the size of LLMs and also more training data, you're gonna see a complete different set of errors. So our methodology cannot be applied to. Is there, okay.
Thank our speaker again.
Yeah, thank everyone.
We're done.
Yeah.